So, some movies to get us going on. We talking about dimensional analysis and how we can use some recipe that we'll talk about today, called Buckingham Pi, to be able to figure out what the dimensional, non-dimensional parameters are that allow us to describe these systems. We'll do it for pipe flow today, but there are obviously systems which are more complex than that, and this is one of those because it's kind of what would be called, I guess, aeroelasticity. And that is just like the Tacoma Narrows Bridge. We talked about there being flow. We talked about there being two major parameters we could worry about. That we had to, for any model, we had to have geometric similarity, scaled down model. Obviously, this is a scaled down model. What is it? Probably 100th scale. I'm not really sure. We had to have what we called kinematic similarity, in that the air flowing across it was at the same Reynolds number, not the same velocity, but the same Reynolds number as the real system. And then if that was the case, we could work out what the forces are applied to it from the Euler number. So those are the three kind of variables. So this is more complex than that, in that you'd also have to get similarity in the elasticity of the bridge. And so that's an extra feature that we'd have to worry about. And so this is a wind tunnel looking at the behavior of a bridge. We showed the Tacoma Narrows Bridge and talked about the idea that if the wind is blowing at such a velocity that it sheds vortices off the deck, top and bottom, on this so-called von Karman vortex street, then if that resonant frequency of that shedding is the same as the resonant frequency of the bridge, then it just puts it in motion. Resonance builds the amplitude of the fluctuations, and ultimately it's a goner. And of course you can change that by you can't change the velocity of the wind that will come across your bridge, but you can probably change the resonant frequency of your bridge by dampening it up, making it skinnier, changing the materials you use, etc. I think they'd use dampers to put extra mass on it somehow. And so the same kind of thing goes when you're talking about other aeroelastic structures, and of course a classic aeroelastic structure would be a plane. And I don't know what this is about the Airbus, I think. A bit of test pilot stuff for the A380, so you know the double-decker answer to the jumbo jet, the 747 that Airbus put together, that now I think they're not manufacturing anymore because they don't the whole airline industry has gone into short-haul flights where you fly on small regional jets, and the big jets that fly between centers are probably adequate if they're just single tier jets, not huge jets with 600 people on them, but jets that carry 300 people like 777s and are much smaller and don't require very specific facilities at airports. And this was a test where, well, I guess they'll go up into the plane, where they're doing, during the test time for the plane, they've got a prototype that flies. The pilot doesn't usually wear a crash helmet and a parachute when you're flying. Commercially, I guess you'd be a bit nervous if they did come on doing that. I also thought it'd be kind of fun to go to a bar at an airport in a pilot's uniform and start drinking. And see what the reaction was. And I think they've arrested some pilots for doing real pilots for doing exactly that. But this is putting it through its tests, and I think in this particular case, trying to get it to actually flutter in flight and stall in flight and do all the kinds of things they would. Obviously, it's not really dimensional analysis, but I think it's an interesting exposition of kind of aeroelasticity, because in these kinds of planes, obviously, it's an elastic structure, and so it can vibrate. And you know from flying yourself that sometimes you get some strange noises and strange vibrations when you're going through turbulence and other things. So, yeah, I'm not sure what they're trying to stall it, and they ended up, as I recall, having an issue with some part of the flesh of the airfoil being ripped off. Not catastrophically, but enough for them to change the design for something. And this, as we come up to 8 o'clock, is, well, you see what it is. An old film, you can tell by the quality of the of the presentation, probably from 1940s. Includes discussion of air elasticity and makes the case, I think, we saw this last time, makes the case that that's exactly what's going on in Tacoma Narrows in the 1950s. And so you know that when you design bridges, you design against that. But you can get flutter in all kinds of things. Yeah, you've probably seen a stop sign in a breeze fluttering. The idea that you can look at planes and understand exactly what's going to go on. If you start some feature in resonance, that's probably not the plane you want to be on in that particular circumstance, because the consequences of it are, if it's too great a flutter, is it puts too much strain on the structure and it falls apart. And even though the stuff that we'll do today is on mundane pipe flow, the same principles that we'll apply to that in Buckingham Pi theorem, space shuttle, looks like a 747. So I guess you want to find the limits of exactly when this occurs, and that's probably not the plane you want to be on if you're flying around for obvious reasons. So although we'll apply it to pipe flow, it's the same idea. You want to make sure that the Reynolds number of the scale model that you're flowing past in the winds tunnel is the same as you'd see in the prototype case. And then if that's the case, then those are the kinds of scaled forces that you'd expect to have on that structure. Whether the structure is the same strength and rigidity as the real plane, I guess, is an extra burden on you to be able to explore, in addition to those kind of fluid mechanics constraints. So that's kind of what we'll talk about in microcosm today. So that's just a preamble before we get on with our details. And yeah, and so this encapsulates what we talked about last time. We made the case, if you look up at the top of this, that these two numbers, Reynolds number and Euler number, are the important parameters. And they're important because we have these three features of similitude for most of the systems that we'll deal with. And that is, we want to get geometric similitude. The model should be a scale model in every respect, in all the lengths. Kinematic similitude is that the Reynolds numbers are the same for the model and the prototype. And if that is the case, then the pressures or forces that you'd measure on your model can be directly translated into the forces on your prototype. And therefore you could compare those with the strength of the prototype. And you might be interested in other things. Of course, this says nothing about vortex shedding, which if you're putting something into resonance, there has to be some feature of the behavior that must relate to that vortex shedding. Nothing about which is said here, but is an extra wrinkle. And so that's what we talked about last time. We made the case that it's really this interplay between Reynolds number and Euler number, defined here as a friction factor, but equivalent to an Euler number, that define the behavior for flow in pipes, where we're interested in the drag on the fluid by the pipe, on flow around objects, like a wind turbine blade, where we're interested in the shear stress that's applied on the wind turbine blade by the fluid. So that's kind of the counterpoint of this, in terms of a drag coefficient or a lift coefficient that says how much lift an airfoil might have. And also when we're flowing in ditches or rivers, where we might be interested in how the shear stress along the side of the bank slows down or controls the velocity in the duct. And so those are the three things that we'll talk about in each of these next 4 weeks, I guess. And that kind of brings us to the end of the class. And so I thought today, rather than going through this, which we have, I might do it in real time, if I can manage that. We'll see if I can try and do that. And so what I'd like to do is go back to this Buckingham Pi theorem and be able to do an example for this geometry and work through the individual components to be able to determine the recipe of how we define what these non-dimensional variables are. So that's my plan for today. And so it's all there written up, but I guess it's a bit crowded with some other verbiage, which perhaps I think is not so useful. So I'm going to find a clean sheet, which is right here, and I'm going to start working on this. So this is what we've just talked about, these needs for these three components. This is Reynolds number, this is Euler number, and if we can define for whatever our system is what these numbers would be, they don't necessarily have to be these, but they turn out to be those typically. For any system you could use, even for understanding the financial markets or for any kind of experiment you want to do, dimensional analysis is an incredibly powerful way of doing it because it basically allows you to minimize the number of experiments that you do. And so I am going to do exactly this Buckingham Pi. I won't rewrite it, but I'll draw the system that we're going to deal with. It's no different from the one that we've seen before. And it will have the same properties as before. There'll be a velocity of fluid coming out, an average velocity. There'll be a length of the pipe, which we'll call L or dl. We've used green typically for our pressure gradient across from upstream to downstream. This is dp or delta p. We would have a diameter of this pipe, which we'd call d. And in here we would have viscosity and a density that would define our system. And do I have anything else I need to worry about? No, I don't think so. Right. And so, what do we want to do with that? Well, what we're going to use for this is we'll use, our ultimate goal is to use our old friend Daniel, but as the energy equation. And so the reason for doing this is that we want to write out P1 over unit weight plus Z1 plus V1 squared over 2G plus the pump head we put into the system is equal to this on upstream and downstream. Remember that we have to write it upstream and downstream, so this would be 1 and this would be 2. Plus H, it's not keeping up with me, HL. And what we can do is if it's a horizontal pipe, then this and this disappear, making life easy for ourselves. If the cross-sectional areas upstream and downstream are also the same, then by definition the velocities have to be the same. And so these terms cancel out. If we're not putting any energy into the system as a pump head, then we end up with P1 minus P2 over unit weight is equal to the head loss. And so I said before that the essence of pipe flow is that these losses that we have in our system, and I suppose we could write it as a summation, are just equal to the change in pressure over a unit weight. Units of length, units of length. So that's really what we were interested in, figuring out that system. And so the bottom line is that we could run an experiment where we flow fluid in a pipe. We measure the pressure drop across the pipe, and we measure the flow rate by flowing it into a bucket or have a flow meter. And then we could do experiments to characterize this system where we know nothing else about it. But we'd like to do as few experiments as we can to describe that behavior. And so what we can do is we can describe the system as something which is, and I'm following the notes that I'm not looking at from earlier on, is that the pressure drop is equal to some function of diameter, velocity, density, viscosity, And that should be it. We use this, typically, I guess we would use something like function of, as in a curly f, but we won't do that here because we use that specifically for friction factor. So this just means function of. And so what we are going to do is we can use Buckingham Pi. We said in this that there are, I should make the point that, so we could also write in, if we wanted to, so these are the parameters: viscosity, density, diameter, velocity, and pressure. You see all these mentioned here. The length would also be 1, except in the book, and just to make this an easier condition, this parameter here is pressure change with length. And so if that's the case, then we don't need to have this here. And so we just need to be cognizant of the fact that this delta PL is a pressure per unit length. And so we said last time that Buckingham Pi theorem says that if we have k independent variables, 1, 2, 3, 4, 5, and we have, did we have n? I can't remember what it was. N units. So these are parameters, and these are units. And units were mass, length, and time, and temperature. We won't use that. So what do we have here? We could identify what these are. This is length over time. So we at least have length over, this is length over time. And this is mass per unit volume. So we have all three. And so we have k minus n dimensionless groups, which is equal to 5 minus 3, which last time I checked is equal to 2. So we have 2 dimensionless groups. So that's our first step. So you can follow the steps in the stuff I've written up in my notes, but this is a bit clearer perhaps. So this is maybe first step. Step 2, choose repeating variables. And so there's kind of an art to this. The dimensionless variables you get will differ depending on the repeating variables you choose. But let's choose diameter, velocity, and density. And these should include all of whatever we have as mass, length, and time. And so they do, right? Length over time and mass per unit length cubed. So what we're going to do is we're going to develop the first, we're going to use these as repeating variables. And we're going to get our first pi group. Call it pi 1. Guess I could make this a bit bigger. And so the idea here is that we'll call this pi 1 is equal to these 3 groups, which will become repeating variables, plus our other 2 independent variables, which is delta PL, and viscosity will be the second one. So this is the one we'll take first. So we're going to make a pi group that's going to include those 4, and that pi group will be delta PL multiplied by D multiplied by V and rho. So these are repeating variables. And I could make it bigger, I guess. Don't know if you need it bigger. And these will be to the power A, B, and C. And this will be to whatever power it is, power 1, I guess. And so what we'll do is we'll define the dimensionless variables that define these. So this will be units of L to the power A. This will be L times T to the minus 1 to the power B. And this will be units of mass per volume to the power C. And I can never, well, we could calculate what this is, but just out of brevity, I'll write it down because I have it written here. This is going to be mass length minus 2, T minus 2. And this is, if you like, to the power 1. And the whole idea of this is that we like this to when we multiply everything out, this will give us a variable which will give us mass, length, and time to the zeros, because that would signify non-dimensions, has no dimensions of mass, length, or time. And so what we want to do is to be able to choose the values of A, B, and C so that we get that. That's really what we're attempting to do. So I will perhaps underscore this with a line. And so we can write 3 equations. We can write those equations in terms of mass. I guess I could call it. We could write them for length. And we could write them for time. And we know that if I just draw this line here, so I'm just going to write 3 simultaneous equations. We want the right-hand side for mass to equal 0, the right-hand side for length to equal 0, and for time also. And we're just going to document which of these parameters exist for each of these features. So we're going to scour these equations now for values of mass. And so if we go through here, this is mass to the power 1. No length, no mass, and mass to the power C. Right? All we're doing is we're summing up the exponents. We're going to do it now for L. We're going to go through this and look at the length terms. And so length is here, and it's minus 2. It's here, and it's equal to A. It's here, and it's equal to B. It's here, and it's equal to minus 3C, right? Equal to 0. And we're going to, I said it properly, but it just was untidy. And then we're going through the third one for time. So time exists here as, again, minus 2. Doesn't exist here. Exists here as minus b. And it doesn't exist here. And those are our 3 equations that we have. And so we're going to solve them. We're going to solve them because C is equal to minus 1, I guess, from the first one. That gives us, we can also solve, this is going to be equal to, B is equal to minus 2. Right? The first one comes from this one. The second one comes from this one, of these 2. And if we know what B and C are in this, we can work out what that would be. And I'll just take it down here. And that is that from that middle equation, A is equal to, apparently, to 1. I wouldn't be able to do that this morning. It's too early. And so that allows us to write out this pi group. Pi 1 is equal to delta PL to the power 1 multiplied by d to the power 1 multiplied by v to the power minus 2 multiplied by this to the power c, which is minus 1. And if we write it out in a more familiar way, it will be delta PL times d divided by v squared rho. And if we wanted to, we could write this out. Remember that this is equal to dp over L. This would be dp over dl d v squared rho. So like magic, we have an Euler number multiplied by a non-dimensional number, which is just d over L, which we'll use later. Okay? So that's the first pi group. So not very good writing. My writing's gone to pot. So we said that we have two potential pi groups because of this. So we have a second one. So we've done it in terms of these three repeating variables and in terms of this parameter here. We can do it in terms of these three repeating variables and this parameter here. So our next pi group, so second of two, and we'll write it out just like this. It's going to be pi 2. We're going to use the new parameter, which was viscosity. I want to, viscosity, keep them both on the screen. These repeating variables, so I can't draw very well this. This is d, this is v, and this is rho. And I can mark them by the same terms, A, B, and C. This is to the power 1. I can be a little bit sneaky now, see if this will work for me. And you'll have to furiously scribble this down. See if this works. Never does it work? Oh, look at that. So we're going to do this. I do this not to frustrate you, but to make it clear that these are going to repeat. I'm going to get rid of some stuff. I'm going to get rid of this because this isn't true. And get rid of this because this isn't true. But everything else should be, right? These are the repeating variables we had before. These are the terms that, the exponents that we've applied to them. These are the units of those repeating variables. And so these have to be exactly the same as before. What won't be the same is viscosity. Viscosity is in units, and I'll just pull it out of the hat here. You know how to do it, right? You know that viscosity is equal to tau dv dx. And you know that tau is equal to a stress, which is equal to a force divided by an area, which is a velocity and a length. And force is equal to mass times acceleration. And acceleration is equal to length over time to the minus 2. And so you can always get this viscosity if you know what the subordinate units are. We did this in the second time we met. And so stress is force over area, force is mass times acceleration, acceleration is this. So all of these are now defined in length over time, length squared, mass, kilograms. So you can do that. And if you go through that, it turns out, trust me, never trust anybody older than 26. I'm just writing it down. I don't remember this from time to time, but this is it. And so if we're doing this, again, we're going to solve this so they equal 0. And if we go through for mass, Mass in this one would be equal to 1. This is to the power 1 as well. Length in this one would be equal to -1. And time in this one would be equal to -1. And so again, I guess we would have, in this particular case, C is equal to -1. Is that right? Take it off to the other side. Plus B is equal to -1. Is that right? And A, if we do it with the rest, I won't do the math. But if we know, so we've done this one, we've done this one, and now if we know what both B and C are, we can solve for A. And it turns out to be -1. And so we can write our second pi group, pi 2, is equal to viscosity to the power 1, diameter to the power A, velocity to the power B, and density to the power C. And if we write it out in a more familiar way, we have mu v rho. Yeah?
For our variables, C and B, I think those are supposed to be -1.
You are right. Did I say -1 but write 1, or did I not? Good. Well, that's at least some recourse for my stupidity. Okay, that makes it even better. So, okay, so let's go back. Let me score this out. And I'll do that. So you're exactly right. Thank you for stopping me. And so C is -1, B is -1, and A is -1, yeah. So this is 1, this is -1, this is -1, and this is -1. And of course it has to be that, because we know exactly, we can guess what's going to come out of this. And it's going to be equal to mu divided by dv rho. And all we care is about the dimensions, so we could also write this as dv rho over mu. So this is Reynolds number, this is 1 over Reynolds number. Yeah. So, and that's it. And so what we have then is we have, if we want to write it out in longhand, we have pi 1 is equal to some function of pi 2. And that is going to be, in terms of the terms that we have, what was it? Delta P over rho v squared, d over dl we called it, equals some function of v rho d over mu. And so we know that Reynolds number, Euler number is going to be in some way connected to Reynolds number. I'm right at the end of my rope here. And so we could draw this same figure that we had before. That would be Reynolds number versus Euler number. And I'll write these out. So this is delta P over v squared. This is v rho d over viscosity. And so what we could do is we could come back to this experiment. So we don't know anything about the system. We haven't got any equations that tell us anything about what's going on. And we take a piece of pipe and we put it so that we run water in that pipe from upstream to downstream. we measure the pressure drop that we apply, and we measure the flow rate that comes out of it as being a flow rate divided by the cross-sectional area. So we get an average velocity, and we get one data point. And so we do an experiment with a pipe of some size, and we get, for a given pressure drop, we get a given flow velocity. Right? So we have 1 point. So we apply a delta P, we get a velocity out of it, and so we know this velocity, we know the density of the fluid, we know the diameter of the pipe, we know the viscosity of the fluid, and we know, and we get V squared. The only strange thing about this is that this variable we get at this output from our experiment occurs on this axis and this axis. So we increase the pressure, and we get another point out of it. And I'm going to draw that point here. Oh, I don't like that arrow. And this point is the second point. So we use a bigger pressure. If we use a bigger pressure, we'd expect to get a bigger velocity. So we'd expect to move in this direction here from this point. But also if we get a bigger velocity, then a velocity squared is going to actually reduce this more than if it was just a linear system. Don't worry too much about that now. I know exactly what this is going to look like. It's going to be a curve that looks like this. It's not necessarily linear, but it will look like this. And so we can do a bunch of experiments that allow us to track this. If we kept on increasing the pressure, so it's kind of counterintuitive, going down here is increasing the pressure because the velocity gets bigger much faster. What we'd see is that this would start, instead of going down here all the way, it would start tracking across here. So these would be the other experiments we get. And so we'd realize that there's something kind of strange with our experimental setup, that this is still a single relationship. It's not a linear relationship. This doesn't have to be linear, but it veers away from it. And it would turn out that if we did an experiment now with something which was much rougher on the inside, and so if this was our experiment with our pipe, and I'm going to draw two of the pipes. And if this particular pipe had some roughness on it that was really kind of small, so in other words, so that this, we talked about it last time, this roughness, which we'll call epsilon, versus the roughness on this pipe, which is much bigger, which is epsilon, which would just be a length. And we also have on this pipe, both these pipes are the same otherwise. They have the same diameter. Then we'd see that if we did this rougher pipe, then the results that we'd get would be some data that would look like this, and maybe it would go across here like this. And so we surmise all of a sudden that there's another parameter that makes some difference in our analysis. And that parameter is that instead of just being a function of pressure, diameter, velocity, density, and viscosity, this is pressure gradient, there's another parameter that belongs on the end. And so before, what we did was we had k equals 5, so k minus n was equal to 2. Now, if we include this extra parameter, which is epsilon, then we have k is equal to 6, and k minus n is equal to 3. And so we have another term, pi 3, that we need to figure out. And so we could go through Buckingham Pi again, or we can just realize that this is in units of length. To make it dimensionless, we can only use something that has units of length only, and the easiest way for us to do that is just do this ratio. So this could be our pi 3 group. And the reason for choosing that is that we'll find that each one of these are for different values of epsilon over d, which is big, and epsilon over d, which is small. And so, if you remember, and I whisk us back to what we talked about last time, we drew all these figures, and we can return to that. These figures that we have here is exactly this. This friction factor is a surrogate for what we've called, it's not the same, it's proportional to, I guess, friction Euler number. And it's exactly this behavior. So in the laminar regime, the flow within a pipe, it doesn't care about the roughness at all. It's completely independent of roughness. So in this, the Euler number, don't have enough space. In this part, the Euler number is a function of viscosity, because that's in Reynolds number, right? Reynolds number is velocity, density, diameter over viscosity. So it's a function of Reynolds number here, right? Because it varies with Reynolds number. And so that is the important feature here. But it is independent of epsilon over d. So it's not a function of that. And in this part here, the Euler number, or the friction factor, is a function of viscosity, but epsilon over d. And we know that because here, this line is exactly horizontal, so it's independent of the Reynolds number you choose, which varies with this, you get the same friction factor on this axis, right? It's a constant. So it doesn't vary with viscosity. It's completely independent of viscosity. But each of these lines, this is for epsilon over d is small. And this is for epsilon, there'd be a line up here for epsilon over d equals large. That's my shorthand. So it doesn't really matter so much about the pipe flow, because you'll see this many times, the fact that it's either laminar or turbulent, and the dependencies of the equation kind of change with this dependency on laminar or turbulent flow, because when you solve the equation that we want to solve, which if we go back to the beginning of what we talked about today, is this. So that what we'd like to do is be able to figure out exactly what this relationship is going to be. And so this is the left-hand side that we kind of have. This is a bit like an Euler number, right? This could be written as delta P just as a pressure change, rho G. We could divide both sides through by, what am I going to want to do? So I could multiply both sides through by G. I could, yeah, it's not going to work out, is it? Yeah, I don't want to do that. I'm not going to do that because this will mess it up. But anyway, so yeah, so this is the rationale by which we can do this. So we know absolutely nothing about the governing equations. We can only surmise that these parameters that we've chosen might affect this system, and then we can kind of group them in a certain way to be able to do this. So what we could do here is, now that we have delta P over rho V squared is equal to or proportional to, and I'm going to write it out, Reynolds number times length over diameter. So I'm just going to take this from one side to the other. And now what I'm going to do is what I was going to do up at the top, and that is I'm going to multiply both sides by v squared and divide by g. And so I'll get v squared over g. And I guess I could divide both sides by 2. And if I do that, then I can cancel out this, and I can end up, if I rewrite this, as exactly delta p over rho g. So this term here is unit weight, is proportional to length over diameter times Reynolds number and v squared over 2g. And the reason I'm doing that is that now, if I go back to the top of this, we had an expression that linked a pressure drop written as a length. So this is a pressure drop written as a pressure head is equal to some number. Let's forget that I did this on the other side. And this is the essence of what we want to determine. And so what we've done now is we have a relationship which we'll use in week 10 and 11 and beyond. And that is that delta P over unit weight is equal to H sub L, which is equal to a friction factor, length over diameter, and V squared over 2G. And this is what we'll use to characterize what this head loss term is. And we know the length of our piping system. We know the diameters of the pipe. We know what the average flow velocity within the pipe is, perhaps. And all we have to do is figure out what this friction factor is. And this friction factor is given by this term here. And in the laminar regime, the friction factor is given for a circular pipe as 64 over Reynolds number. And so this term here will turn out to be 64 over RE when it's laminar. And it will be something else when it's not laminar. And so this is the basic expression that we will want to use. And so the main point from today is that starting out with a system that you can only guess the behavior of and physically hold in your hand in an experiment, you can make a best guess about what the physical dependencies of the parameters would be that would affect that system. And if you can define them in terms of all those parameters and the numbers of units that they represent, there's a recipe that you can apply to be able to go through them. And so there's always a question about this on the third test. You're always given the variables, and you're always told which ones to use as repeating variables and which ones to use as the dependent variables. Because if you choose different variables, you get subtly different results, but you kind of end up with the same overall conclusion, but you end up with maybe different groups in terms of the reciprocal of one, different terms mixed up. And so you're always given that. But the main message from this is not to confuse you, but merely to make the point that this very powerful method, that if you know what the rough parameters which you think might control your system are, then you can group them so you can do a minimum number of experiments to be able to explore your system, and from those minimum number of experiments be able to define those dependencies without ever knowing what the Navier-Stokes equations are or what solutions to those equations are as well. When we talked about the Navier-Stokes equations, we converted them into the equation for flow within a parallel-sided duct and also flow within a tube. And we ended up with some relationships. Importantly, those relationships were only for this regime, the laminar regime. And so the equations that we developed, which were actually basically this expression here, were only for the laminar regime. And so if we wanted to figure out what the behavior is once we start going faster in the tube, there's nothing in those simple Navier, complicated enough as they are, Navier-Stokes equations, there's nothing in those equations that would tell us that this behavior would happen, because this behavior isn't locked in. It's not described in those systems. The behavior that's represented in the systems is just that Newton's law of viscosity holds. So the Navier-Stokes equations assume this relationship. This doesn't conform to this. This is turbulent flow. This assumes that within the pipe, if you look within the pipe, every single particle that you have moves directly downstream from that point at some given velocity. It'll be zero velocity at the edge, and as you go across the width of the pipe, it'll be this parabolic shape. So these will be the individual velocities. If it's turbulent, then the behavior you get across the pipe is that this velocity here might take some detours. And so it turns out that the profile actually for fully developed turbulent flow is much closer to a uniform flow, because all the single particles are doing this random walk type thing. And so if you look in macro scale, they all seem to be moving in general at the same rate right across the pipe. In laminar flow, the essence of laminar flow is it's zero velocity at the wall of the pipe, and it's a maximum velocity in the middle. And so we wouldn't get this behavior otherwise. So that's it. So one, I guess, parting grace would be, you know, if we looked at these behaviors, when we looked at the behavior of an airplane before and tried to look at the behavior in a wind tunnel, right? So we did this airplane, and we did this real airplane, and we did the example to link them together. What we did was we said that the geometries of these two should scale exactly, geometric similitude. We said that the Reynolds numbers should scale. So the Reynolds number for the model should equal the Reynolds number for the prototype. So in other words, that means that on this graph here, which we've just kind of looked at, would be this number that we go up to some place. And we know that if the only other term governing behavior is the Euler number, which allows us to figure out what the pressure would be on that structure, then if there are only two terms, then the relationship between those terms must look like this, which is really what this is drawing. It doesn't have to be a straight line. It could be a straight line. It could be a curved line. It could be anything you want. I guess what it can't be is it can't be this, right? Because you end up with multiple values for any given value. So it has to be some kind of relationship. And so if the relationship is this, I don't know if it's a straight line or not, all that we're saying about this system where we have two parameters is that you end up, if we know this curve, then, and we know Reynolds number, then both for the model and for the prototype, same Reynolds number, and therefore the same Euler number. And that's really what we did. If there are more than two terms in our equation, as there seemingly are here, then that translates to this, maybe. And so in what we've just looked at, this third pi group would be our values of epsilon over d equal to 0.1, epsilon over d equals to 0.01, epsilon over d equal to 0.001. So that's because we have 3 pi groups. We have Euler number, we have Reynolds number, and we have relative roughness. And so again, we have curves for each of these parameters. But again, if we get, what do we call it, kinematic similitude, that the Reynolds numbers are the same. Reynolds number model equals Reynolds number prototype. That's this curve here. If we know what the physical constraints of our system are, then that defines this point here. And then that gives us an Euler number, which is the same for the model and for the prototype. And so we've done an experiment on the model at the same velocity that the plane is going to fly at. So we know what this number is for our model. We know what the geometry and roughness of our model is. So we know we end up at this point. And so we know what the value of the Euler number is. And so we know the velocity of the model. We measure the pressure on the model and the density of the fluid flowing around the model. So we know everything about this number. And what we don't know here is we have P rho v squared. We don't know what the pressure is, and we'd like to find that out. And so that's our last remaining variable. And so that's it. It's an incredibly powerful technique that we've used in terms of this. I'll note that in previous years on the recorded videos, I've gone through a couple of examples. I thought the example we went through of the plane that we went through early on, which we've just really repeated here, was useful. But there are a couple of examples here that are also recorded in previous videos if you want to look at them. This 7.54, which gives an example of how to use Buckingham Pi, where instead of using mass, length, and time, we also said there's another system which is force, length, and time. So forces, viscosity is newtons per meter squared seconds, Pascal seconds, right? So it's much easier to do the units, right? You know for sure that viscosity is in Pascal seconds, which is going to be in units of newtons, force, which is newtons, pascals per meter squared, length minus 2 times time, which is exactly what this is. So you don't have to mess around with mass for this particular one, but you end up with similar variables. And one that also does an example, if you have a dish that you have wind blowing over at 80 kilometers a mile, and you have a wind tunnel, which is a 5th scale model, and you measure the forces on this, how do you convert those forces to the real dish to see it doesn't fall over? And it just uses exactly the same thing. It uses something called kinematic viscosity, which is equal to dynamic viscosity. Kinematic viscosity is equal to dynamic viscosity divided by density. So this is what we've called, I never use it, this is dynamic. So anyway, so if you want to look at these, we won't have time to go through them today, but they exist. And so it does the same thing. It looks to see that the model and the prototype are running at the same Reynolds number. This is just Reynolds number model equals Reynolds number prototype. So you figure out exactly what the model velocity should be. If you know what this model velocity should be, you run your experiments at that model velocity and measure the forces on it. And then you look at the Euler numbers for the model and the Euler number for the prototype. This is just a, This is just a force divided by the diameter of the dish. So this is like a pressure. This whole term here is a pressure divided by rho v squared and half in there. Doesn't matter about the halves. So you measure the force on the model going at the velocity of the model and the diameter of the model and the density of the fluid that's going over it. I think it might be something other than air. No, it is air. And then you know the density of the air going over it. You know the velocity in real life, and you know the diameter of the real model, and the only unknown is the force. So that's it. That's it. So anyway, that's it. So dimensional, the inappropriately named dimensional analysis, which is really analysis with non-dimensional variables. But it gives an interesting way to be able to look at these fluid systems. And can be applied in any branch of engineering. You'll find that pumping test solutions for groundwater flow, pumping test solutions for petroleum reservoirs are all cast in terms of non-dimensional parameters, which would come out with exactly the same techniques that we're using here. So it's throughout engineering and science, this idea of using non-dimensional parameters is a very, it's a key tenet, I think, that you'll see elsewhere in your careers. Okay? All right, that's it. We've gone 5 minutes over.